Okay, now this is another one of those organic questions where we start with a molecule and we have to deduce its formula, and it gets converted into B and C here through reflux with sulfuric acid. Now we notice that the number of carbons has changed, and that we've got 6 in B and 3 in C, so that's seems like a form of hydrolysis, and because it's acid hydrolysis. So it seems likely that what we started with is an ester, and that got split up, but we check as we went on. Now B and C then react to make D and E with dichromate, so some kind of oxidation's going on there, you would think. And as neither D or E react with toluenes, then we haven't formed a aldehyde. Now when B, which is the one with 3 oxygens in, so that's probably a carboxylic acid, reacts with concentrated sulfuric acid, it produces 3 structural isomers, F, G and H, with the molecular form of C6H10O2, all of which are optically active. And F exists as geometrical isomers. Now that means that we've got a double bond in there, and that would also mean that probably when we look at the starting formula here, if this is an ester, which I'm assuming it is at the moment, we've got 3 oxygens. Now only 2 are required for an ester, so one of the other oxygens could in fact be an OH group, and so when that reacts with dilute sulfuric acid it won't react, and so that means on B, as that's the one that goes through this, so it's a way of probably identifying where the OH group is. If we can figure out F, G and H, well then we'll, on the information given, then we'll probably have a better idea of what B is. And the best thing to do with this is to get started. So let's look at this in a bit more detail. Okay, now really just all I've done here is write out that information. We started with A, and we undergo what I'm assuming at the moment is acid hydrolysis to make these two. They undergo oxidation to make D and E, but we don't get an aldehyde. And probably the hardest thing at the moment is to sort out the 3 different isomers that have that molecular formula. F can be a geometrical isomer, G has no geometrical isomer, and while an F and G will decolorize bromine water, H does not. Okay. Now, the fact that H does not obviously infers immediately that there is no double bond here. And as we started with 3 oxygens here, and we use concentrated sulfuric acid, and it seems likely that on this we have a OH group, an alcohol group, which can be removed by elimination, and we're going to get a major minor product, of which we would assume that F and G are those. H would be the problem, but when we realize that the kind of little trick here is just remembering that if we have an acid group and an alcohol group present, which we assume we do on this one, on B, that if we add concentrated sulfuric acid, it's possible we'll form an ester, and that would be the 3rd one. So the only condition we've really got to meet in this is to make sure they're all optically active. Now I'm not going to worry about D and E at this stage, because once we've been able to identify B clearly, that will give us D, and C should also be reasonably straightforward. So we're going to concentrate on F, G and H. Okay. Now, if we were to draw out C6, 1, 2, 3, 4, 5, and 6, and O2, so we're going to have an OH group coming off there somewhere, you should recognize pretty quickly that no matter where you put the OH group, if you then undergo elimination and form a double bond anywhere in here, that is not going to form a structure that is optically active. Having a side group, like a methyl group, will be the key in creating optically active structures. So this chain is one that's not going to work. Also, having the OH group here means we can't really have a double bond form here because there's no there's no hydrogen attached to this carbon. So that seems an unlikely spot to have the OH, so we'll have to shift that along. Now we also need to consider the methyl group, which I've just initially put here. Obviously it can't go on the end because it's just extending the chain. And as I've said, we can't have the OH group here. If we put the methyl group immediately here and we have a double bond, that immediately means we can't have a optically active structure, because the double bond basically means you can't have a chiral carbon there. So the methyl group and the OH group need to be separated for that to happen. Anyway, I'll show you what would happen if we did, for instance, OH, CH3 group. We'd have a double bond here. This can't be the chiral carbon because, well, there's a double bond there. This can't be a chiral carbon. This can't. So having these two adjacent isn't going to work, because as soon as you have the OH there's a possibility of having a double bond between those two carbons. So they need to be separate. So if we shift the OH along, again we can't have the OH at the end because that means only one double bond can form here. That really only gives one possibility in terms of an isomer. So really we're looking at the OH being here. So let's try that. Okay, now let's try this one. So if we undergo, so we've got the OH group here, we've got the methyl group here, we've got 6 carbons, so let's try react. Okay, so if we look at the structure here, as proposed one, we then just, again, trial and error. Is it going to work? Well, if we undergo elimination, we get the OH and we need an H next door, so either here or here. And the major product, by the way, would be on this side as the pore gets poorer, which is this one here. That would be the major product. This would be the minor one, but we get a double bond on either side. Now, in this one, because we've got an H here and a CH3 here, and an H here, and then this other group here, this can actually exist as a geometrical isomer. It does exhibit optical isomers. Just a minute, I just forgot to draw an H in there. So I'll just draw one in there as well. And this one, though, as soon as you see the two H's, does not exist as an optical isomer. Now that means this is F, and this is G, and then obviously this is B. Now we've got to determine H. Now H will just be using B with this OH group here, which is going to react, sorry, not with this OH, sorry, that's going to be removed with the H of here, and we're going to basically get, you know, this joining around on this side and forming a ring. We just have to draw that correctly and make sure we do a good job of that, and that will be H, so forming the ester. So those four we now know, and we should be able to work backwards and figure out the others. Now all I've done is draw them out again. So this is just B, which we just, you know, kind of worked out from above. F, which is the one that can exist as geometrical isomers because it's got you know, 2 different groups on the each side of the double bond. It's asymmetrical as well. G, and they're all optically active. We've got a chiral carbon there and a chiral carbon here again, and this cannot exist as geometrical isomers because of this. Now to draw the ring structure, it's just taking care as you go around. All I've done is start from you know, the carbon with a double bond here, so I started at this point and just moved around, drawing it, but going around in a circle. Now when you get to the end here, obviously just take care of this OH, which is going to form the single bond right here with the oxygen, that there's this methyl group here, and that's what this is here, just sticking out in space, because the join is going to be between you know, this carbon to this oxygen to this carbon, say. So without getting into reaction mechanisms on which H2O gets removed, just in terms of drawing it. Now that's all those 3 structures. Now we're going to go back from that and have a look at the original one. Now, going backwards, if we look at this, this was B. So this was when A was refluxed, which is an ester. It made this, and it also gave off a smaller group, which had an OH group on. We know that because it reacts with dichromate. So the OH group can either be in the middle or it can be on the side. Now, this is where it's a little awkward, because we're told, the only information we're told to give us information on where that OH can be is, whether it's a primary or secondary alcohol, is that it does not react with toluene, so there cannot be an aldehyde group. Now, typically primary alcohols do react to make carboxylic acids, but it's also likely that we'd get some aldehyde present. So in theory we'd probably get some kind of positive result for that if we reacted that. And to get absolutely nothing, we can only infer one thing, and that is that the OH group must be in the middle, and from this we should now be able to get structure B and then structure A as well. And before we look at structure A, if we were to react D, and this is structure C here, that's just the alcohol. If we were to react these with dichromate and get D and E, then obviously this would just end up very similar, except we'd have a ketone there, and still have the methyl group, of course, and this would not react with that. And E obviously is just going to change into a propanone. So we just now have to go backwards and draw A, and we're finished with this question. So that is E, that is D, and let's get A. Okay, now A is actually in its own way quite awkward to draw, because you want to draw things in a straight chain, but because the OH is there that's formed, that means that this must have been the O that was bonded to that carbon there. So just make sure you get that right. And this final structure, of course, is A. So just take a little bit of thought, and after you've drawn the structure, perhaps think what would happen as you go through that sequence, and make sure you've got the right carbons. Also make sure you've got all the hydrogens. I tend to miss out that one for some reason. Just do a quick review to make sure it makes sense as you go through that, because having to go backwards and work things out, it's very easy to make a mistake. Okay, and that's that question.